So, good afternoon. Welcome to Advanced Modeling Methods. Let's write it down. And today is lecture 14. So, we've basically formulated the boundary element methods, at least its basic form, for heat conduction problems, in general for potential problems. Okay, I call it heat conduction because it's just one application. But anything that's governed by the Laplace equation, which can be ideal fluid flow, it can be anything that has to do with potential theory, gravitational force, heat conduction, and so on. Anything that's governed by the Laplace equation can be solved with this framework and this formulation that we presented in the last few lectures. So we talked about discretization, we talked about three types of elements. We talked about how to handle those matrices and then how to rearrange those matrices to solve the system, to get the T's and Q's on the boundary. So then we can take those T's and Q's on the boundaries to calculate anything we want in the interior or anywhere else, for that matter, because that's what the boundary integral equation does for you. And we showed, using a very simple MathCAD code, that is very powerful. Okay, that with very coarse discretization, you're able to attain very accurate solutions, at least accurate with respect to an analytical solution that we derive for a special case on a square. So I posted project number 2. Okay, I gave you 20 days or so to turn it in, because it's due actually exactly 21 days from today. It's due in 3 weeks from now. And I gave you that much lead time, although you don't need anything else from what we have done up until this point, for you to digest it, for you to try to analyze and basically learn how to implement this. You're welcome to use the MathCAD code that I posted for you to solve that problem, although you're going to have to make major modifications to that to make it applicable to that problem. Or you're welcome to use what I'm going to be working on today, which is basically a code that I have pre-built for you with certain limitations that I left off on purpose for you to be able, because you have to do something, right, for the project. I just set up the problem. All right, and I'm going to tell you what are those limitations. So basically what I wanted to go over today was just the implementation of these very simple framework for boundary elements on a high-level programming language. In particular, I want to talk about a Fortran code that I wrote for you. And it's a stripped-down version of a much general-purpose code. Different versions of codes that I've been working on for many years. This one basically works on a single domain, okay? And a single domain can be of any shape, of any size. There's a little preprocessor attached to it. It does many things automatically for you. All you have to do is specify what the geometry looks like, specify the boundary conditions, and it'll solve the problem for you, okay? You also have to specify the discretization that you want, how many boundary elements and so on. It basically uses one single type of element, which is the quadratic subparametric elements, okay? So the boundary elements are allowed to curve because they're quadratic or parabolic splines, but the field variable, temperature and flux, are modeled to be constant within each of the elements. Okay. Now, I understand a lot of you are not very familiar with Fortran. Fortran is not a language that is very popular. It's actually exclusive for scientific programming. It's the only thing that it's used for. And that was the idea behind the conception of Fortran. Its name is Formula Translator, so it's basically from design, a programming language that was conceived to deal with just scientific programming, and that's it. It's a very simple programming language. It has very few statements and very few operators. And with a combination of those, you can write very complicated logic. Okay? It is a procedural programming language as opposed to object-oriented, like C++, for example, is object-oriented. As a matter of fact, C++ is what's called a hybrid programming language, because you can write procedural code in C++. You can also write object-oriented code on C++. Programming languages such as Java, for example, are purely object-oriented. Okay, you have to write classes, and then you have to call instances to those classes, and so on. We're not going to get into that. We just want to write just number crunching code. We don't care about writing windows and interfaces and nice pictures and all that. We use other type of programs to handle that. What we just want to do is number crunching as efficient as possible, and that's what Fortran is good for. Okay. Now Fortran has gone through many changes and evolution over the years from the conception, which was back in the mid 50s. So it actually predates C by over, what is it, 16 years. C is from 1971. Fortran from 1955. So it's actually contemporary with programming languages, just Ada and COBOL and other different purpose programming languages. So it was actually, as I said, written for this purpose. Since the 1950s, this has evolved into the first unified syntax accepted by IEEE, was by ANSI, I'm sorry, not IEEE. ANSI is American National Standards Institute, or Numerical Standards Institute, National Standards Institute. And it was 1966 when they approved the first standard. Okay, so regardless of the company who wrote the compiler, whether it was Borland or whether it was IBM, they had to actually attach to these standards. So they finally basically wrote a cohesive set of rules for determining what was accepted and as programming syntax. Then it went through more evolutions, and in 1977 came the second generation called Fortran 77, and that's the one that's most popular even up until today. 1977 caught on so much that it's still used today. I've actually moved from 77 to 90 to 95 to 2000 and everything, but I end up always going back to 77 because it's just so simple to program. You pretty much don't have to remember anything. It's just, it becomes so natural because it's just plain English. You just program the 12 statements that it has, and with that you can construct any logic you want. So you'll see today that it's very easy to understand, much easier than any other programming language. All right, and the reason why I use it is because it's very efficient. Once you write a program in Fortran, you compile it, you link it, you create an executable file. That executable file can actually be in any architecture. Well, obviously we're going to do it on Windows. We're going to do it on 64-bit for 64-bit processors. Well, you can code on Fortran for the Mac, or you can code on Fortran for Linux boxes. And there's free versions out there. The GNU library offers you a free version of it's called G77 instead of F77, or G90 instead of F90. There's also Intel produces the most powerful one, and that's the one I use, the Intel compiler. The Intel compiler uses the Microsoft programming environment, the Microsoft shell, which is called the Visual Studio. And then in the Visual Studio, you can just edit your code, and then once you compile and link, then that calls the Intel. It's a very optimized linker that produces a very efficient executable. And then once you run that executable, as a regular binary for your architecture, for your Windows machine or Linux or whatever, you will notice it will run 50 times faster than maybe if you do it in MATLAB, for example. It doesn't have the overhead associated with running a program in MATLAB. So if you want to write serious code, you use high-level programming languages. Okay? MATLAB is a great tool, but it's not a tool to program things of this nature. Not something that you would use to program something that would eventually have maybe hundreds of thousands of unknowns, degrees of freedom, because you have large matrices, you have to handle large memory spaces and so on. And that would, when you're talking about orders of magnitude in efficiency, and I'm not talking just about one order of magnitude, I'm talking about 2, maybe 100 times faster, then you don't want to wait 100 days. You're okay with waiting a day for an answer. You don't want to wait 100 days. So then it becomes a difference. All right, so what we're going to do is an implementation of 2D heat conduction, boundary element method EM formulation using high-level programming language. And in this case, we're going to use Fortran. And in particular, we're going to use the Fortran 77 syntax. It's also called the fixed format syntax. All right? So the way we're going to structure this code is as follows. We're going to have the following subroutines. We're going to have a main code. And the main code is basically where we set everything up. We declare the variables that we need. We declare the variables that have global scope or local scope, the size of the variables, and so on. Then we're going to have certain subroutines, one of them being the input subroutine. Well, the input subroutine is where geometric and field information is read into the code. Okay, and we're going to do this by means of an input file. So you, the user, you're going to write an input file where you're going to describe the geometry and the field, basically boundary conditions and so on. And then this routine here is going to read that file in that specific format. Then we're going to have a routine called preprocessor subroutine. That subroutine takes on this geometric information and this field information, and it creates boundary element discretization, and it creates boundary conditions. Okay? Uses geometric and field information to create boundary element discretization, boundary conditions, and internal points for post-processing. Okay, why do we need to generate internal points when internal points are not really necessary to do anything within the framework of solving a problem with boundary elements? Well, you're given a problem. You're given a problem and then you solve it, and what does solving it means? It means getting temperatures and fluxes on the boundary. Okay? If you want to display where your temperature contours are or what your flux vectors are, you cannot do it with just that information, right? You need information inside. So the information inside is going to help you construct a heat map, and it's probably going to help you help us construct a vector plot. All right? So we need internal points just for post-processing so that we can output the results. By the way, the output and visualization of results is going to be done outside of Fortran. In Fortran, we're not going to write graphical user interfaces, right? It's not meant to do any of that. We're going to output information to another format that we can read with another code, maybe Excel or something else, where we can display the information. We're not going to use Excel, we're going to use something else. All right. After these, we have a collocation subroutine. And the collocation subroutine basically generate G and H matrices. That's all it does. It collocates on the boundary nodes, it integrates, and it produces all the influence coefficients for G and for H. And we need a solution subroutine. And the solution subroutine is essentially going to use this and the boundary conditions. So uses G and H and boundary conditions to form A x equals B, right? Solves system. So it solves the system AX equal B. And computes additional T's and Qx, Qy at internal points. All right, so this routine takes G and H, the boundary conditions. It regroups everything. It takes pieces of G, pieces of H, and puts it into A. It takes the remaining pieces of G and H, multiplies the boundary conditions, and gets B. Solves a system of equation, not by inversion. We're going to use another technique. And then once it has all the key T's and Q's, solving the system means finding T's and Q's, then it computes the additional internal T's and Q's. And then finally the output subroutine. Writes T and Q as well as internal T's and Qx, Qy's. Remember that internally you don't have just Q, you have Q as a vector, so you have the X component and the Y component of that vector, to a text file and to a tech plot formatted file for contour and vector display. That's what it does. All right. Let me also tell you about a couple of peripheral subroutines. And these peripheral subroutines I've taken out of libraries, mostly. I didn't write this myself. These are necessary to complement the code. For example, how do you solve the system AX equal B? Actually, first, before we get to that point, there's a routine that I wrote called in or out subroutine. This subroutine determines whether a given point is inside or outside the boundary gamma of a domain. Why is that necessary? Well, remember that we're generating internal points. arbitrarily, right? For display purposes. But let's say that your geometry is not, the geometry you want to set up is not regular. Let's say it's a triangle. Well, you just throw in a bunch of points, right? But you have to decide which ones to keep and which ones to discard, right? And this routine will take care of that. This routine basically will determine that, and it will determine that by simple approximation. If you think about it, it's not easy, it's not trivial to decide whether a point is inside or outside a particular domain. A domain that is bounded by a boundary gamma, okay? You can do an angular search or an angular summation. If you take a domain and a boundary and you put a point inside, the sum of the angles with respect to all the points on that domain should be 360. And if the point is outside, the sum of the angles is supposed to give you 0. Okay? So you can do a bunch of, you can calculate, decide a bunch of points, calculate a bunch of angles. The points you already have because you already have the discretization of the boundaries. Right? So you can go point by point on the boundary, calculate angles. You sum all those angles. If you get 2 pi, that means you're inside. If you get 0, that means you're outside. If you get pi, that means you're on the boundary. Exactly. Okay? That's one way. But then that means that you have to calculate, you do arc cosines and arc sines, you have to make certain decisions. The technique I use is slightly different. I basically use the approximation of an integral around the boundary. Okay? Remember, you just basically use the integral of the Dirac delta function, which we've talked about many times. I use the integral of the Dirac delta function of x xi, and xi will be the point that you're testing, and that would give you 1 if xi belongs to omega, and 0 if xi doesn't belong to omega. And how do we carry out this integration? We basically say, well, we know that this is equal to the Laplace of the Green's function, because we know that the Laplace of the Green's function is equal to the Dirac delta function, actually the negative of the Laplace of the Green's function. And applying Gauss' theorem, so you say I of psi is equal to this, which is equal to this, which now is equal to minus the integral of the so basically the integral around, I'm sorry, this would be the integral around the contour, the boundary of h of x and xi dxi. So all you have to do is take the function h, which we already have because we need it to generate the influence coefficients, integrate it around the boundary elements, and this integration I approximate. And if you get 1, that means that it's outside, it's inside. If you get 0, that means that it's outside. Okay? So you basically use the same boundary element discretization that you have. Another routine is LU factors and LU solve or LU back. This is part of the LU decomposition routine. This is part of numerical recipes. This is part of numerical recipes. It's just to solve a system of equations, right? It basically says that if you have AX equals B, which you can solve by inversion, you can invert matrix A, which is very inefficient, and it's also very inaccurate because it has a lot of round-off accumulation. You can also do Gaussian elimination, you can do Gauss-Seidel, you can do all other indirect methods. LU decomposition basically lets A be equal to the product of L times U, such that L is a matrix that is lower triangular, and H is a matrix that is upper triangular, So it's basically the composition of a matrix A broken up into two, and to the product of, I'm sorry, not H, this is U. U. One is lower triangular, the other one is upper triangular. So basically you get LU times X is equal to B, right? So then you multiply these two and you get Y. So that means that L is equal to Y. So we're going to let this one be equal to Y. Is equal to B, which you don't know. Remember, you're looking for X, and therefore you don't know. If you don't know what X is, you don't know what Y is, but you're just calling that Y. And this you can solve very easily. Because it's a lower triangular matrix, it is already decoupled. Okay, that means that the first equation has a single unknown, the second equation has two unknowns, the third equation has three unknowns. So you can solve the first equation, then use a solution to solve the second. This is easily solved, right, by back substitution. And then you have U times X is equal to Y. After you solve for Y, you can put it in here and then now solve for X. Well, the advantage of something like this, there are many advantages. This is more efficient than inverting the matrix. It is as efficient as Gaussian elimination. It requires n-cubed floating point operations to get to an answer. But the big advantage of these is the process of decomposing the matrix, you do once, and then keep those LU factors, right? And let's say you decide to change the right-hand side because your boundary conditions change, right? Or for some reason you decide to change the right-hand side, you don't need to decompose A again. A is already decomposed, okay? So in order to get the new solution for a new set of boundary conditions, remember that the matrix A contains pieces of H and pieces of G. And that's just geometric information, right? As long as you don't change the geometry or the discretization, A is not going to change. The boundary conditions are embedded in here. If you change the boundary conditions, you have a completely different problem, right? But you don't have to decompose the matrix again, that's already decomposed. All you need to do is perform the back substitution twice. Yeah, well, backward and forward substitution. Actually, forward and backward substitution, that is. Which is very efficient. It only requires n floating point operations. That happens just like that. So changing the problem will be very efficient to get an answer if you use this routine. So that's why I decided to go with this one. Another routine is quad pack. D QX subroutine, and this one is from quad pack, and quad pack is from one of the national labs, Argonne, no, not Argonne, Livermore, no, not Lawrence Livermore. What?
It's Livermore.
Is it Lawrence Livermore?
Yeah, I think I remember.
Okay, so one of those one of those national labs, and it's not the only pack that they put out. They put out a pack called LinPack, which is a linear system solution package. They put out something called ODE pack, which is a package of routines to solve ordinary differential equations. They put out a bunch of packs. And this one in particular solves, or basically the integral from a to b of fx of f eta d eta, and provides error estimate.
Let's say minus a is 6.
I'm sorry, from A to B. Just from A to B. So you specify the limits of integration, specify the error bounds, tolerance, and it'll give you an answer and an error estimate. And it uses obviously Gaussian or Gauss-Kronrod quadratures. Yes.
So this is the same. So this would be another solution routine as opposed to LU.
No.
Okay. So
No, LU decomposition solves the system AX equal B. Before you can get to that, you need this. But you need to perform integration so that you can form H and G. And with H and G, then you form AX equal B. All right. Another routine that I use, I don't remember where I got it from, but there's plenty out there. Triangulation. Subroutine. This one uses that Delaney triangulation. So it basically polygonalizes the points. Okay, you have points on the boundary and points on the interior, and then it produces a bunch of triangles, right? To polygonalize the geometry. Why do we need to do this? Just for display purposes. Okay? We don't need this for the solution process, just for the display purposes. Okay? So basically it triangularizes, it polygonalizes boundary and interior points using Delaney triangulation algorithms. For display purposes. Or TechPlot format. And by the way, TechPlot is a software that is installed in all the computers here in the College of Engineering. It's just a post-processing software. It reads data from Fluent, from ANSYS, from CATIA, from anything you want, and it displays it for you. Basically, it has a lot of freedom as to the way you can display. You can make movies, you can take cuts, you can do whatever you want. But part of its format is that it requires triangularized data. You cannot just give it scattered data. You cannot just say, well, here are some points on the boundary, here are some points in the interior, display. It doesn't know how to do that. It does have an internal triangularization routine, TechPlot does, but then you have to go through the process of doing that every time. So in order to avoid that, I've used a triangulation routine to create the triangularized data, that means connectivity between points to form triangles, and export that to TechPlot so that TechPlot automatically displays the data for you on any computer on campus. So you can produce contour plots and vector plots and so on. All right, so that's it. That's pretty much it. There's other functions and things inside the code that you will see, but are mainly basically just structuring the code. For example, the Green's function, I put it inside a function. The derivative of the Green's function, the calculation of the normals and things like that, I put into separate implicit functions. And that's it. All right, so let's go to, this is not right. Okay, let's go to the computer. And let's go to the PC here. All right, but before I show you the code, I want to show you the project number 2, in case you haven't seen it. It's already posted on Canvas. I actually already solved it. And here it is. So it's a 2-dimensional steady heat conduction problem on this particular stainless steel element. The conductivity of stainless steel is 14.7. Okay, so it's basically a steel plate with a little bump. This is mostly signifying something like a heat sink. Okay, it has cooling channels. We're passing water through these cooling channels. You don't have to worry about the water or anything like that. You just have to assume that, well, let me show you. There's a boundary condition there on the interior walls of the cooling channel. These dashed lines means that this is insulated, right? This is perfectly symmetric with respect to this vertical line. It says so here. Okay, so this is a 2 by 2 square dot, 2 by 2 square dot, 2 by 2 square dot. And this is just a cut. Let's just assume that this is very long in this direction. That's why we can afford to do a 2D problem. All right? So the assumption here is that we have, this is insulated here, or embedded, and this is your domain, this is your boundary. It goes like this, like this, like this, like this, like this, and like this. And the boundary continues here. However, here, because this is a hole, you have to go clockwise so that the normal point's inside. Okay? You define your boundary here counterclockwise so that the normal always points outside. And when you get to a hole like this, you have to go clockwise so that the normal points inside the hole, which means outside the domain. Right? So the idea is that, well, the concept of this problem, this is a standard heat conduction problem within the stainless steel element, is that there is a hot fluid passing through here. You have different film coefficients, right? And it's assumed that the flow comes in this direction. This film coefficient is low, then it gets very high, then it gets low because separation, and then it gets the same as this one. It's just a parallel plate, heat transfer coefficient. All right? And then this is just forced convection, and this is liquid, so this is a higher film coefficient, a higher heat transfer coefficient that is removing energy. So this is a hot temperature, and this is a cold temperature. Okay? However, this is not a first kind boundary condition. Okay? The only two boundary conditions that we've implemented are what? Temperature and heat flux. Okay? Now we have a third kind boundary condition. I'm going to explain you in a minute. And that's basically the only change that you need to make to the code. The only change you need to make to the code is how to implement that third kind boundary condition. That's it. Other than building the geometry in an input file, which is you can do in 15 minutes, it would be about implementing that third kind boundary condition. You have second kind here, second kind here, second kind here, Q equals 0. But you have third kind here, 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 and here. There's no first kind boundary condition anywhere here. However, you can test it before you do anything to the code. You can test it assuming that this is first kind, first kind, first kind. This is all at T infinity H. This is all at the hot fluid temperature, and this is all at the cold fluid temperature. So you put type 1 here, type 1 here, type 1 here, and type 1 all around. Just to test that your geometry is correct before you do anything to the code. Okay? I recommend you do that. Alright, so what else? Well, this is governed by the Laplace equation, the temperature it is. And remember the third kind boundary conditions obey Newton's cooling law, which is basically that the heat flux is proportional to the temperature on the boundary at every location through the film coefficient H, which can be rewritten. Remember that Q is equal to minus K dt dn, so all of these can be rewritten this way. So basically there is a linear relationship between dt dn and T, and that's how you're going to rearrange your matrix system when you have a third kind boundary condition. Is that clear? Now you gotta do some derivations by hand and so on. It's not terribly difficult. It's just adding a couple lines to the code, either the math code or the Fortran code. I'm giving you the values here. 10,000, 1,000 is the temperature on the top. 0 is the temperature through the cooling channels. These are the four heat transfer coefficients on the top surface. It goes from 50, 500, 10, and 50 again. This is all in watts meter square Kelvin. This is all in SI units. Be careful with the geometry that's in centimeters. You need to convert that to meters. Okay? And the heat transfer coefficient along the cooling or through the cooling holes is 5,000 watts meter square Kelvin. So you're going to solve this using boundary element codes that I provide, using just quadratic subparametric boundary elements with 3 levels. You're going to do 1 centimeter elements, 0.5 centimeter elements, and 0.25 centimeter elements. So you're just going to do the input file 3 times. Just going to change a couple numbers in the input file. It's not a big deal. And you're going to model. You're going to model these semicircle with 2 parabolic splines. One that goes from here to here, and one that goes from here to here. And that's not very difficult either, because I've already built the preprocessor for you. All you have to do is specify the 3 points, right? And specify these 3 points. That's one spline, that's another spline. Just got to find the coordinates of those points. All right, and you're going to do it with those 3 discretization levels. And by the way, on those splines, you're going to use 7 elements, 14 elements, 28 elements for each spline in each of the 3 discretization cases. and solve the problem. Once you get a solution, you're going to plot your contours of temperature, contours of the heat flux vectors, and so on. But you're also going to calculate the amount of heat that is added through the top surface and the amount of heat that is removed from the cooling holes. Okay? That is a way of testing convergency, by the way, because what is the relationship of the heat that is being removed from the heat that is being added?
Should be equal.
It should be equal, right? This is a steady problem with no generation. So at steady state, those two have to be identical because the other boundaries are insulated, right? So the amount of heat or amount of energy that is added through here has to be identical to the amount of energy that is removed from here. Okay? So all you have to do is take out the output file, look at the Q's, multiply each Q by its own length, add them up, and multiply each Q by its own length, add them up. You do that in Excel or you do it by hand if you want to. But remember, you're going to have like 30 or 40 of them depending on what discretization you use. And then calculate the amount of heating and the amount of cooling. They have to be the same. They're not going to give you identical. But the larger the discretization, or the finer the discretization, the closer they're going to be to each other. And that's what you're going to test here. Is that clear? All right, and then your report has to contain, these cover pages are signed with your name, your hand derivation, printouts of the 3 input files, printouts of the 3 output files. Then you plot temperature contours with heat flux vector plots for the 3 discretization levels, including a contour legend and a table. I'll show you how to do that in a minute. And a table with the requested heat flow values for the 3 discretization levels: QS, cooling, and QS heating. All right. I'm sure you're going to have questions, but let's leave that for another time, and let's just go straight to lecture 14. So I'm gonna zip all of these and put it up for you to download on Canvas. So basically, I created the program, and it's called Lecture 14 Visual Fortran Project. Okay. So this is basically the project which combines all these source files together, links them together. Okay. This project has a bunch of source files. All Fortran files, co-location, fundamental, in or out, input, everything that I talked about. Okay? The quad pack, LU back substitution, LU factors, so on and so forth. Alright? But we don't need to open them one by one. All we need to do, by the way, using the Intel Fortran compiler, which is on every computer on my lab, you can go there, unzip that file, discharge the file to your local computer, and then you double click on the project, Visual Fortran project, and it will open the project for you, which means opening all the files that are associated with each other, that are linked together. So these are all the Fortran files, including the main, input in order, right? Main, input, preprocessor, co-location, solution, and output, right here. And all the peripheral ones, in or out, integral, the fundamental, which are the fundamental solutions, right? Where all the functions, fundamental solutions, the triangulation, and the LU, the composition. All right, so let's look at the main code. This is the main code. By the way, the main code, every file includes a code called parameters.4, okay? And that is the file that has, instead of me writing everything on every one of these files, I have it into a file called parameters.4, and that's the file that sets the limits for how big the problem can be. So if I go to parameters, where's parameters? Here. This is parameters. The number of splines maximum, and your preprocessor can only be 100. You can change that to whatever you want, but if you do, you have to rebuild the code, okay? Because I use static memory allocation. Basically, I tell the matrices how big they have to be at programming time, and then compile the code. I don't let that change as I go, or at runtime. This is the maximum number of boundary elements is 1,000, so we can do a problem that has 1,000 elements, but if you want to change that, you just come here, change it, and rebuild the entire code. The maximum number of nodes, that includes boundary and internal nodes. This is not necessary. This is not necessary. I don't know why I have it there. Actually, let me delete it to avoid confusion. Okay, save it. And the value of pi. The value of pi is the arc cosine of -1. Okay? Now in Fortran, the d in front of every function means double precision. So this is the arc cosine function, and the d in front of it means it's do it in double precision. And the argument, this is -1 double precision. I'm specifying that this is a double precision number because in Fortran you have to be specific. If you just say -1, it's going to assume that this is a single precision number, and it's going to calculate the cosine of a single precision number, and then it's going to convert that to double precision because you told it it was double precision. It's less accurate. But if the argument is already expressed in double precision, this is just scientific notation for -1 and double precision. This is like saying to the 10 to the power of 0. Okay? If I say -1 without the dot, I'm basically saying that that's an integer, and that's even less precise. So Fortran, you have to be very specific. So if you go back to the main code, every file calls that parameter. Every file you open is going to call that parameter as .4. In the main code, it's probably too big. Let me go to the fonts here and reduce the size. Okay, it's probably better. So these are all the global variables. I use global scope variables so that I avoid having to pass them as arguments to all the subroutines. Okay, so I just generate these common blocks. This is the information, for example, number of boundary elements, number of nodes, the properties, thermal conductivity. I don't use K for thermal conductivity because in Fortran, variables that start with the letter I, J, K, L, M, and N are reserved for integers. Everything else is floating. It's just float. And by the way, I use a statement here called implicit, where I say that every variable that starts with an A through an H is a double precision variable, or any variable that starts with an O through a Z is a double precision variable. Because in Fortran, I don't have to declare every variable I use, like in C. In C, you have to declare every variable you use and have to say what type it is. In Fortran, you don't have to, but if you have this implicit, it already is going to assume that anything that starts with an A through an H is double precision. O through Z is double precision. All right, so more information is, for example, the segment information, the splines, right, for pre-processing, the geometry of the splines, the condition, the boundary conditions on the spline, then the boundary information. The preprocessor routine is going to take that spline information, it's going to generate boundary elements, and remember the coordinates of the boundary elements, you have as many as MB max boundary elements, you're going to have as much as NB in a particular application. And every boundary element has 3 locations. First point, second point, and third point. Okay? There are 3 nodes that describe a boundary element. The boundary normals. So this is a normal vector at the center of each boundary element and the length of each boundary element for display purposes too. We don't need that during the calculation. Boundary conditions, the type. See, this starts with a K. That's the type of boundary condition. 1 is temperature, 2 is heat flux, and 3 would be convective, but that's not implemented. The boundary condition value and the H value, which is not implemented yet, that's for you to implement, but I added the variable there so you don't have to create a new one. The geometry in terms of nodes, maximum number of nodes, XC and YC. That includes all the nodes, including boundary nodes and interior nodes. That's also for display purposes and for post-processing purposes. The matrices G and H, see, they're the size of the number of boundary elements. The transformation, that's for the coordinate transformation to perform integration when you have a segment in space that goes from x1, y1, x2, y2, x3, y3. And remember, that's mapped into something that goes from -1 to 1 in eta space. And it also has a collocation point xi, yi. That information is held here and passed through the fundamental solution routines. The solution on the boundary, T and Q, and the solution in the interior, TC, QX, and QY. And here are the 6 routines that I talked about. There's some writing on the wall. This will be written into the console. BMHD2D, boundary element method for 2D heat conduction, this class, this department, this university. Anything that starts with a C, by the way, this is Fortran fixed format. So anything that you write from the column 7 to the left is considered to be a comment. The compiler will only compile and interpret anything that's written from column 7 all the way to column 72. You cannot go past column 72, you cannot go past or before column 7. That dates back to the old days of punch cards. So the punch cards had actual limits and through which they can read. So this dates back to that time. Called input, that's a subroutine. Okay, the only argument that I'm sending there and receiving from is the title. Call preprocessor, call collocation, call solution, call output. That's it. So if you go to the input routine, I basically only pass the common variables that are going to be used in this routine, not all of them. I'm only going to be used the properties and the segment information or spline information. Okay, nothing else is going to be read from this file. So I open a file, which always has to have the name, by the way, the input file always has to have the name bemht2d.imp. That's what I decided, okay? And it always has to be in a subdirectory called data relative to where the executable is located, okay? So your input file has to have that name and has to have a specific format. The first line is going to contain the title, maximum 120 characters. Second line, the thermal conductivity. Okay, you cannot put anything else on that line. Third line, the number of segments or the number of splines that you want to define your geometry. Okay, if you want to define a square, you need only 4 segments. That other one that we're the project, it might need I don't know, a couple dozen segments to define, because each cooling hole requires 4, right? Then you read the segment information. So you loop from 1 to the number of segments. You're going to read the segment number, how many nodes or elements you want per segment, okay? Because every segment is going to be broken up into pieces depending on the discretization level you use, and the 3 coordinates of every segment or every spline. So every spline is going to have 3 coordinates, x, y, x, y, x, y. And it's going to draw a parabolic spline through it, and it's going to discretize this many times. It's going to do it for you. And then it's going to read the information about boundary conditions for every spline. So again, read on the following lines, as many as number of splines, the spline number, the type of boundary condition for that spline, if it's first kind, second kind, or third kind, 1, 2, or 3, the boundary condition, and H, the film coefficient for that spline. And that's it. If it finds an error or something, it just writes to the wall, input file does not exist. And that's it, and then it closes the file. That's all that subroutine is. Then the subroutine that follows that after input is the preprocessor. The preprocessor subroutine uses that spline information. So it uses the spline information to generate X and Y boundary element discretization, the normals, the boundary conditions, and the interior information. Okay? And here it is. First, it builds boundary data. It goes through some algorithms that you can just take your time to read. It just basically goes through all the splines, uses the discretization of every spline, and uses a quadratic shape functions, same quadratic shape functions that we've been using, to put in boundary elements. And that's it. I already tested it, works fine. And it does so, and at the end of the day, see, it is increasing a counter called NB. That's the number of boundary elements. So the number of boundary elements is basically going to be the number of splines times the number of boundary elements that you specify for each spline. After it does that, it also positions the boundary conditions on every spline, right? Because you can specify a spline that goes from here to here, where the temperature might go from 0 to 20 to 80. And it just basically does a quadratic spline distribution between 0, 20, and 80, and it positions those values along all the boundary elements. for boundary condition and for H, which again, you don't have to worry about transforming that, you just have to worry about the moment of implementing them in the system. So then it calculates the limits and average spacing in order to throw in internal points. So it takes the geometry, calculates the maximum value of X and the maximum value of Y. So it has limits, and then it throws in a bunch of points, assuming that the geometry is a square, right? So you embed the geometry, whatever it is, into the smallest size rectangle that you can embed it, and then it throws a whole bunch of points in there. And it throws points depending on the discretization level. So it calculates what is the size at which every point is separated from each other, the average size, and it's going to use that same average size to throw in internal points. Okay, so the higher the discretization you use, the more internal points it's going to throw in, just to keep some sort of consistency. So it builds internal nodes. So it does what I just told you, using those limits and those average spacing, del X and del Y. And also, for post-processing purposes, it takes every boundary element, just for post-processing purposes, and moves and shifts the nodes that is at the center of each boundary element to the end, right? Because remember, the BM, the way we set it up using subparametric elements, is going to calculate the temperature and the heat flux at the center of each element. We cannot send that information through a triangulation routine. The triangulation routine is going to need the vertex values. So what we're going to do is we're going to position also boundary nodes at the end of each element. Okay? So part of the internal information is also boundary information. But it's boundary information that is not necessarily at the center of each element, but it's at the vertex of each element. Is that clear? Okay. So it's going to generate internal data plus additional boundary data just for post-processing. And that's it. So back to the main code. That's the preprocessor, and then it does collocation. The collocation routine is quite simple. It uses information XY to generate a G and H. That's it. That's all it does. So it basically loops from I equal 1 to number of boundary elements and J equal 1 number of boundary elements. Notice the collocation point xi, yi is the center node of element I. And we're going to integrate x1, y1, x2, y2, x3, y3. We're going to integrate along element J from first node, second node, and third node for the mapping, right? Now, let's not pay attention to that if, but basically it just says integrate from -1 to 1, right? Integrate from -1 to 1. Call the routine dquax with the function g and with the function h. This is the fundamental solution and the normal derivative of the fundamental solution, which I have here in this routine called fundamental. Integrates it between this limit of integration DLA and DLB with these error, absolute, and error. Those are the tolerances that I specify upstairs, and it returns an error estimate and the number of divisions that were necessary and some information that we are not going to need. Okay? And then it puts that result inside Gij. And it puts this result inside of Hij. Now, there's an if condition there, that if I is equal to j, remember what happens when the collocation point coincides with the integration point? You have a singular integrand, right? So in that case, you don't want to integrate from -1 to 1. You want to break up the integral into two. One that goes from -1 to 0, and another one that goes from 0 to 1. So the limits of integration are broken into two. One that goes from -1 to 0, and the other one that goes from 0 to 1. And you don't worry about calculating the h integral, because that one you're going to calculate with equipotential theory, right? You don't calculate HII, you only calculate GII. At the end of these loops, you calculate HII by the sum of the off-diagonal, by the negative of the sum of the off-diagonal, and that's it. That's the collocation routine. Go back to main. Now we have the solution routine. In the solution routine, oh, by the way, the integration is here. And I don't expect you to, this is a very long routine that does adaptive Gauss-Kronrod integration. It takes any function f from a limit a to a limit b with an absolute tolerance and a relative tolerance. It produces a result with an absolute error, a number of intervals, and an error code. That's all. Okay? What happens internally? It uses pairs of Gaussian quadratures and Cronbrook quadratures to produce an error estimate. If it needs to break up, it breaks up so that it satisfies its tolerance and this tolerance. That's it. And the tolerance that I always give before calling this routine is 10 to the minus 6 for both. I want the error to be at most 10 to the minus 6, relative and absolute. So if you go back to the collocation, notice that before I even started the loop, I specify EA and ER. The absolute error and the relative error to be 10 to the minus 6. All right, now go back to the main code. The main code calls now solution. The solution routine is going to take H and G and the boundary conditions. It's going to rearrange H and G. See? Shift columns of G and H depending on boundary conditions. If boundary condition is type 2, shift the column, the negative of H, and put it back into G, and take the negative of G and put it into H. For the entire column, from I equal 1 to MB, for all the rows of column J. That's all it's doing. If the boundary condition is type 1, you don't do anything. Okay? And if the boundary condition is type 3, which is not implemented here, you're going to do stuff. If KT J is equal to 3, then and if not here. Do stuff. Okay. That's the one I want to pose for you. You need to do something there to rearrange H and G. So notice that I'm not forming A because I don't want to create a new matrix in memory space. I don't want to waste memory with another matrix called A. What I'm doing is I am interchanging columns of H and G and putting everything back into G and everything back into H. Alright? You're going to do the same, slightly different, when the boundary condition type is equal to 3. Then it performs LU decomposition. It takes the matrix G, which is now A, right? So I've basically assembled A with parts of G and parts of H. Perform LU decomposition, that's in here, and LU factors. Right? So this basically takes a matrix of size NB, and it performs LU decomposition, and this variable here called index is where it stores information about the column shifting and row shifting. It is necessary for when you do the back substitution later. Okay, now it changes the flux boundary condition to normal derivative, because remember when you specify flux, you're specifying minus k TDN, but this framework, this formulation solves it assuming that it's just the TDN. So it is changing a flux boundary condition to a normal derivative boundary condition. Alright? It forms the right hand side vector B by combining what was left of H and G, which is now part of H, times the boundary conditions. Alright? And then it performs the solution of the system by back substitution. It takes the decomposed matrix G. So now G, after decomposition, contains pieces of L and pieces of U. It contains LU within the same matrix. You don't need two additional matrices because half of that matrix is 0 and half of the other matrix is 0. The size, the index of shifting, and then the right hand side vector B. And then the solution, you don't need another vector called X. The solution is going to be placed here into B. Here we go. And then, if the boundary condition type, you loop through all the elements, if boundary condition type is equal to 1, then the temperature was the boundary condition vector, and the flux is the B vector, the solution X. Boundary condition type is equal to 2, then T is the B vector, the solution vector, Q is the boundary condition, and then if KT J is equal to 3, then stuff, and if. Alright, so this is skeleton for you, from the beginning and from the end. Alright, there it is, there it is. That's the only place where you have to do anything to the code. Those lines, those two lines right there. Now it's going to compute, once it has Q's and T's and Q's, it's going to compute temperatures and fluxes on the internal points. And that includes the additional boundary points that are not at the center but at the end nodes. So notice I am placing the limits of integration from -1 to 1 and the tolerance absolute and relative to 10 to the -6. It goes through the collocation process again, it performs the integrations, and it does the job. Alright? And that's all you have to do. All you have to do is modify those two. The final routine is output. The final routine is output. It basically uses T and Q, right? Solution on the boundary. It uses TC, QX, and QY, that's a solution in the interior, and it generates an output file. It generates two output files. The first one is a text file called BMHC2D.out on the same folder where the input was. Same name, just different extension, right? And that file is going to contain the title, it's going to contain the number of boundary points and the number of internal points, right? Number of boundary points and number of internal points. And then it's going to contain information about the boundary results. That includes the position of the location of the elements, the 3 nodes of each element, and the temperature and the flux at that element from 1 to NB. And then it's going to do so also in the interior. So that's the file that you have to use to calculate those fluxes, to integrate the fluxes along the heating surface and along the cooling surface. And in the interior, it's just going to put in internal point, temperature, and the components of the heat flux. And then it's going to generate an extra file, but before it does that, it triangulates the information. It basically takes all the number boundary points, all total number points. It takes XC and YC, okay, the locations of the nodes, takes the normal vectors, and it generates a mesh, a triangular mesh. And then that triangular mesh and that information about temperatures and heat fluxes is going to be output or written into a file called bmhc2d.plt. This is the default extension for techplot files, which every computer on campus or in the college has. So you just double click on that file and you can plot the contour and the vectors. So don't worry about what it does, just trust me. Alright, so let's build this. Okay, if I want to compile a specific file, I just do Ctrl F7, or just go here and build and compile. And then if I want to build solution, it basically takes all the compiled files and it links them together into a single executable, which I've already given the name BMHC2D. It succeeded. It built a file called BMHC2D. So here, see where the Visual Fortran project was. It produced a file called BMHC2D.executable. Right? And it's going to try to read from this directory called data. And in this directory called data, I've already created an input file for you. You can use this as a test. This input file does heat conduction problem on a square. It has this is the format of the input file that we already specified. Thermal conductivity 1. It has 4 segments. 1, 2, 3, 4. Yeah. Segment 1 has 20 nodes, or we want 20 elements in that segment from 0, 0, 0.50, 1, 0. That's the bottom of the square. Spline 2 has 20 elements. It goes from 1, 0, 1.05, and 1, 1. So that's the right side wall. So it does a square on a counterclockwise basis. Okay? And then I'm imposing the boundary conditions for the 4 segments. First segment is insulated. Type 2, flux is equal to 0. Okay? Second segment on the right hand side, type 1, temperature at the bottom right corner is 0, temperature at the center of the right wall is 100, temperature at the top right hand corner is 0. That is the exact same problem we solved with MathCAD. Okay, we want to see if we can do it here. We can replicate the same solution. Temperature is equal to 0, temperature is equal to 0 on the top surface, and heat flux is equal to 0 on the left surface. Okay? Is that clear? Alright, so that's all you need to solve a problem. And basically run this code. As long as the name of the file is bmhc2d.input and is located in the data directory relative to where the executable was, you just execute, it's Ctrl F5, and that's all it took. That's 80 elements and 400 points that I put in internally. Let me show you real quick. So I produced a file called output. The output file has information about the problem, the title, number of boundary elements, number of internal points. It has a location of all the boundary elements, x, y, x, y, x, y, the 3 nodes, the temperature and the flux. Okay? And then after 80 lines, for this particular case, it's going to have internal results. 1 through 400, x and y, temperature, qx and qy. Okay? In addition to that, it has this template file, which has that triangularization. So all you have to do is double click on it. And it will open Tekla for you. And every computer on campus has Tekla 360, which will recognize that file. Alright? So that's a square. That's the triangularization that it produced on the square. Every one of these center vertices is an internal point, as you can see. And if I want to plot the contour, and I want to hide the mesh, I want to plot the contours of temperature, that really looks like the solution that we solved in class. Okay? I can go here to field, contour, levels, and increase the number of levels. Right now it has 15. I want to go to 51. From 0 to 100, I know the minimum is 0, the maximum is 100. I want 51, so I have a little bit more resolution. I want to get rid of those axes. I want to see those axes. Get rid of that. Let's say I want to plot vector. I want a vector plot. The x-coordinate is going to be qx, and y-coordinate is going to be qy. And that's a vector plot. But those plots are small, those vectors are small. I go to field, vector, vector length, and let me make that, I don't know, 1e minus 0.3. Well, it's too much. Vector length 0.04. That's better. So it does what it's supposed to be doing. It's heating from here. Okay, the temperature is high, it's heating, it's going in this direction. All the flux is going up, the temperature is equal to 0 here. There's 0 flux here, because I imposed a adiabatic condition, and 0 flux here. And there's a little recirculation of the flow here, which we found in the analytical solution as well. Okay? And I can change a bunch of things here. But if I don't want to go through the process of selecting colors or anything like that, by the way, you can put a legend. If you go to field, contour, legend, and I want to show a contour legend, that legend is here. It's too large, so I want to skip a label. There it is, from 0 to 100, that's a legend. You can make it vertical or horizontal. If you don't want to go through the process of recreating all this and setting up the colors and the size of the vectors and the legend and adjusting size and so on and so forth, you can save a layout. You can go File, Save Layout As, and it basically saves all that information as to how you set up this problem. And I've already done that for you. I don't want to save this. I've already done that for you for this particular problem. So if you open the layout, that layout file is going to open that template file. And it's going to display everything with the format that we've already employed. There it is. Okay. Any questions?
Just one quick question, does a Fortran compiler from a particular year work with a particular year of Visual Studio? Because I had like Fortran compiler at home and I was trying to run it with the recent version, like 2015 Visual Studio. And then
No,
it went,
the Visual Fortran
Uh-huh.
doesn't exist anymore.
okay,
Visual Fortran was originally a Microsoft product.
right,
Well, it was originally a digital. Digital went out of business. Compaq bought it.
Mhm.
It became Compaq Visual Fortran
Mhm. they
version
got another
5.
name now, I don't know what they call it.
Then
XP?
after Compaq Visual Fortran, Microsoft had it, and then Intel is the one who writes it now. They just use the Visual Studio. The shell is Microsoft.
Okay,
The Visual Studio, the environment is Microsoft,
Mhm.
but the compiler is made by Intel.
because I put the compiler from Intel
Mhm.
into Visual Studio 15 and then it had some issues.
No, that's not gonna work.
It's gotta have,
It's only gonna do C++ and C.
yeah, you need like an older
Yeah.
version, but I don't know
Yeah.
what year of
The
Visual.
10, 2010.
2010.
But it comes with the shell itself. The,
Oh, so
the Intel compiler comes with the Microsoft Visual Studio shell.
Okay.
You
so
don't need
good.
to install Visual Studio.
Oh, okay.
All right. Any questions? All right. So I'll post this on Canvas for you to have, and well, good luck with this project.
3 weeks.
Yep.